Have you ever really stopped to think about the ground you're standing on? What if I told you it's not solid at all, but constantly in motion? Today, we're diving into the colossal hidden forces that literally move our world. Let's get into it.
It's kind of wild to think about, but for the longest time, the accepted science was that our planet was basically a solid, motionless rock. The continents were where they were, and that was that. The very idea of a world in constant motion, pure science fiction. That was the bedrock belief.
Yeah, they were completely, and I mean utterly, wrong. Big discoveries like seafloor spreading and the whole theory of plate tectonics just shattered that old model. It revealed a planet that is unbelievably dynamic, both on its surface and deep, deep down.
So that brings us to the big mystery for today. If entire continents are on the move, what kind of engine is powerful enough to do that? What generates that kind of titanic force? Well, to find the answer, we have to look down, way, way down. Okay, so our first stop in this investigation is finding the power source. Because, without an engine, nothing's gonna move, right? All that incredible energy needed to shift tectonic plates around, it comes from the immense heat trapped inside the planet's core and mantle. You can think of it like a giant furnace at the center of the world, and that furnace is what's fueling all the geological action we see up here on the surface.
So where does all this heat come from? Well, it's mainly from two places. First, you've got the slow, steady decay of radioactive elements that are just scattered all through the Earth's mantle and crust. And second, there's what we call residual heat, basically the leftover energy from the planet's super-violent formation billions of years ago. Put them together and you've got yourself a planetary-sized furnace.
Okay, so we've got this massive furnace, but how does that heat actually move stuff? This is the crucial part. A geologist named Arthur Holmes had a brilliant idea. All that heat creates what we call convection currents. Hot material rises, it cools off near the surface, and then it sinks back down. This creates this super slow but incredibly powerful circulation in the mantle. The best way to think of it is as a giant planetary conveyor belt. And the tectonic plates, they're basically just along for the ride. So we found our engine, these convection currents, but now we have to figure out exactly how that power is transferred to the plates. And this is where it gets really interesting, because it brings us to a kind of tectonic tug of war, with two main suspects in the lineup. In one corner, you've got a force called ridge push. This is basically gravity giving the plates an outward shove away from these high mid-ocean ridges where new crust is being born. And in the other corner, we have slab pull. This is the powerful downward pull of a cold, super dense plate as it sinks back down into the mantle. And you can see how this works right here. On the left, that's ridge push. It's kind of like a gentle nudge, pushing the plate downhill from that spreading ridge. But then, look over on the right. That's slab pull. That's where the edge of the plate is literally diving back into the earth, acting like a massive, heavy anchor that's pulling the rest of the plate along with it. So the big question is, which one is the true heavyweight champion of plate tectonics? Is it the push from behind or that powerful pull from the front? Which force is really doing most of the work to move our continents? Well, after decades of debate, research, and running all kinds of computer models, the scientific community has a pretty clear answer. It's time for the big reveal. And the evidence, it points to a clear winner: slab pull. Now, don't get me wrong, ridge push definitely plays a part, but the overwhelming consensus now is that slab pull is the main driver. That pull is just way, way stronger than the push. And if you want to understand why it's so much stronger, you've got to look at what's happening right here, in what we call a subduction zone. Let's break this process down because this is where all the action is. It all happens in a few key steps. First, as that oceanic crust moves away from the ridge where it was born, it cools down over millions of years, getting older and a whole lot denser. See where this is going? Eventually, it gets so dense and heavy that it literally starts to sink back into the mantle. We call this sinking edge a slab. And once that heavy slab starts sinking, gravity just takes over, pulling the rest of it down with immense force. That powerful downward tug is what drags the rest of the vast tectonic plate across the Earth's surface. It's an incredible process. So, there you have it. Case closed, right? Slab pull is the big boss. Well, not so fast. Like any great scientific theory,
plate tectonics still has a few lingering questions, a few little mysteries that keep geologists up at night.
Yeah, I mean, the slab hole theory is fantastic. It explains so much. But, like in any good detective story, there's still a few clues that don't quite fit the picture, a few geological observations that don't add up perfectly.
For instance, if slab pull is the main driver, why are there way more spreading ridges around the world than there are subduction zones? And why does most of that subduction, the sinking action, happen just around the Pacific Ocean, while the seafloor is spreading in all the oceans? And what about mountains? How does the theory explain mountain ranges, like the ones in Australia, that are nowhere near an active plate boundary? And finally, this idea that plates are these perfect, single, rigid units, is that really true? Some evidence suggests they might be a little more complex. Now, these questions aren't failures of the theory, not at all. They are the frontiers. They're the exciting, unanswered puzzles that are going to drive the next generation of geologists. They're a great reminder that our planet is this incredibly complex, dynamic system, and we've really only just scratched the surface of understanding the forces that are constantly reshaping our world. What new discoveries will finally solve these planetary mysteries? We'll just have to wait and see.